Thank you very much, Kiarash, for accepting my invitation, giving a talk pretty much last minute because our speaker for this week actually canceled his talk. So I had to rush to find another speaker, and I want to thank Kiarash that even with few days of preparation, he accepted to give us a talk today so that you guys still continue like Efficient ML seminar series. Well, let me give you a brief introduction about Kiarash. So he did his studies in, if I'm not mistaken, electrical engineering,
That's
and then later on computer science, right? And then, he's graduated from the Imperial College London, and then about 2 years ago joined Huawei Noah's Ark Lab in Montreal. I was privileged to be in his interview at the time. So thank you, Kiarash, for joining us and being our colleague and our supporters during the last 2 years. We are looking forward to hearing your talk today. To you, Kiarash.
Okay. First of all, hello, everyone. And thanks, Vahid, for the kind introduction. I'm also honored to be working with each other. Well, today I'm going to talk about one of our recent work at Huawei Montreal on federated learning and multi-objective optimization. This work is a joint work with Zhou Hu, Guojun Zhang, and Professor Yaoliang Yu. Okay. So a large-scale network of connected devices provide access to an unprecedented amount of data. Smartphones, smart homes, self-driving cars, they all collect data that are often private in nature. Traditional machine learning algorithm required all the data to be collected in a central server, and then we can run our algorithm on top of that. Well, you can all imagine that there are lots of challenges in practice for doing so, such as data privacy, data security, and communication costs, just to mention few. Well, one solution for this problem is to use federated learning. Federated learning provides a platform for edge devices to train a central model without sharing their local data. Basically, the first federated learning algorithm has been proposed by a team of researchers from Google in 2016. And since then, there has been a growing interest in this field. In the first glance, federated learning looks like a normal distributed optimization algorithm. However, there are many aspects that distinguish it from the rest of the distributed optimization problem. For example, here, the problem is massively distributed. Just imagine that we want to learn a model from the data on the cell phone users in a city. We are talking about millions of users. The data distribution is non-IID. I will talk about this later in more details. Here we have limited communication. In distributed optimization problems, we are more concerned about the amount of computation that we are doing on each node. However, here our bottleneck is more on communication side, because modern neural networks or model deep learning algorithms, deep learning models, they have millions of parameters, and transferring these parameters over the communication channel is costly. Also, the data distribution is unbalanced. Different users have different amount of data, which also this makes the problem challenging. Regarding the application of federated learning, it can be used for on cell phones, on smartphones. For example, to train a next word prediction in keyboards, smartphone keyboards. It can be used for most of the terminal devices, network traffic management, connected vehicles, and lots of other applications in healthcare and advertisement industry. To start, let's take a look at the simplest federated learning algorithm and the initial federated learning algorithm, which is called FedAvg. As you can see it here, FedAvg is a synchronous distributed algorithm in a sense that in each communication round, the server sends its current model to a set of available devices, and the user, after receiving the model, use their local data set in order to update the model. And for doing so, normally they run a couple of iterations of gradient descent or stochastic gradient descent to update the model. And at the end, they send back the updated model or the gradient or some sort of update back to the server. Here, I need to mention that you can see that and the server takes an average of the received model and update the global model. Here you need to mention, I need to mention that when I'm talking about the gradient, it can be easily seen that gradient that each user sends back to the server, unless we have the assumption explicitly that the data set are IID distributed among all the data, among all the users, the gradient here for user one can have no idea about the rest of the gradients, and this is problematic. We will see it later because it causes lots of issues. And this is not true, and we cannot easily assume that the data distributions are IID, which is totally unrealistic. Also, let's take a look at the challenges of federated learning. The first one that I have already mentioned 2 times is statistical heterogeneity of data, which happens due to different users generating a different type of data. To make this clear, consider that, again, the task of learning an image classifier from the images that users have on their cell phone in a city. We can easily imagine that different people have different type of data. Some people might like to take family photos. Some people like to take photos of their dog. So we cannot assume that the data distribution or the type of data we have on different users have this IID assumption. So this is why this is problematic. Why? Because it's violate.
Kiarash, may I ask you a question here before we go further?
Sure.
The scenario that you are like pushing forward is like sort of edge devices that communicate to a certain server. But would it be the problem for the centralized training too, when you have GPUs that each one of them perhaps required to compute gradient independently, and the server is like the communication will be there as well, but to a motherboard? So would it be similar or different in certain scenarios?
It depends. It depends on the data distribution. Okay, normally what you are saying, it's true for all the distributed algorithm. However, we have normally in a server, we can shuffle the data, we can mix them, or even if we cannot do that, we do not have the communication bottleneck. In the next slide, it's became clear that if we don't have a communication bottleneck, we can train the problem like a centralized problem, and this data to be locally biased toward each user is no longer an issue.
Okay, thank you. Sorry for interruption.
No, I'm glad. This is, I mentioned that this is problematic. Why? Because it's violate the standard IID assumption in statistical learning. We all know that when we are doing like empirical risk minimization, all of these things, or test set, training set, or in-sample, out-sample, all of this concept, we have this notion of IIDness. However, here we no longer have that, and this poses significant difficulty in formulating the goal in precise mathematical terms. Another issue is robustness against adversarial attack. Here, because of privacy, the server cannot check the the system or the process that generate the gradient or gradient update. So whenever some gradient or some information comes to the server, it has to trust it. Traditionally, in distributed optimization, there are some algorithms. They are called Byzantine robust algorithm. Basically, they try to, they imagine that there are some of the nodes are faulty or even adversarial, and they try to come up with some robust way of combining the received information to get a good result. And most of them can be seen as a kind of a anomaly detection. Just to make this clear, what are the problem here? Consider that we have these gradients that we receive from the users, and we use one of these anomaly detection algorithm, and we find this area as a trusted region. We can see some points are out of this region. The first thing is, are they really an adversary? They might belong to some users with some rare information. And for now, just let's imagine that this is true. They are adversary and we get rid of them. The remaining question is, can we really trust the data that are in this trusted region? My short answer is no, because there are new types of attack on federated learning system, which are called model poisoning attack. And they can, because they participate in different rounds, they can predict this behavior or this defense mechanism, and they can adjust the value of their gradient or their position in that space in order to bypass this anomaly detection algorithm. How they do that? Basically, they train a model W on a healthy or clean data set. And then they train a model, like let's say it's an adversarial model, delta, on some poisoned data. And then combine these two, add these together. And by using this M, they can control how much they deviate from the normal behavior. And they have shown that this algorithm are successful can successfully bypass most of the Byzantine robust defense mechanism. Another issue is ensuring fairness among users. We have different age group, different region with different internet speed. There is a whole different type of users, and it's really important to have an algorithm that is fair toward all of them. And also reducing communication costs is another challenge. Just to make this clear, when I'm saying communication cost, what kind of communication and how much we can reduce it. To understand this, and also this, the first scenario answers one of Vahid's question, is that consider the following two scenarios. The first scenario is the server in each communication round ask one user and ask that particular user to use one of its data point to update the model and send back the updated model back to the server. And the server repeat this process until convergence. You can see that this case is totally similar to a centralized training. It's like running stochastic gradient descent. So the performance is good. There is no gap between the performance of a centralized training and federated learning. However, the disadvantage is we have high communication costs. The second scenario, which is ideal for federated learning, is that the server in each communication round in parallel sends its current model only once to a group of available users, ask them to fully learn model, basically learn the model until they satisfy some criteria or they find a stationary point, and then send it back to the server. And the server uses some mechanism to combine this, to aggregate this received model. We can see that the communication cost here, it's minimum because we only, the server only once communicate with each user. However, the downside is this algorithm, the performance is not good. To understand why it's not good, just consider this simple case of only having two objective function or two users, blue user and a green user, which this curves show their loss function or their objective function. And for simplicity, we consider the loss functions are convex here. And this red one, it's the sum of these two loss functions. What we want to minimize the summation of it, the red one. So the solution that we are looking for is X star, and X1 star and X2 star are stationary point of each user. we can see that by using FedAvg and only averaging these two values, we can get some results that are not good. In practice, to mitigate this issue, what they do, most of the federated learning algorithm, they try to find the right balance between the local computation, basically how far they progress toward their local solution, and the amount of computation, and the amount of repetition they send their model to the server and receive the updated model. And basically, federated learning algorithm, they try to find the right balance between these two cases. Okay, with this introduction, let's define our problem. We want to minimize a function f of x, which is a weighted sum of a sum FIIX, and FIIX represent the loss function of each user. And we define it in this way: is an expectation of the loss function of the user with respect to the local data samples. And for each user, we consider some data distribution or some data set which not necessarily they are similar to each other. We make no assumption about the local data set. In the literature, there are different suggestions how to find these weights here. For example, some papers suggested to use the amount of this, the data each user has divided by the total number of the samples, or some people suggested it's better to consider all users equally important and use 1 over m, which m is the total number of the user as a weight. However, is this all we can do, or is this the best thing that we can do? Because there are lots of issues, as I have already mentioned: rare data, uncertain amount of data, fairness, adversary. So there are different, this is not the only formulation for federated learning. We have a different type of formulation. For example, we have agnostic federated learning, which propose to optimize the worst case loss instead to ensure more fairness. Basically, here is a FI loss function of each user, and they suggest to solve this minimax problem, which optimizes the worst case loss. Just remember this. We will come back to this agnostic federated learning later. Or another example, they propose to optimize this Q-fair objective function instead of this simple objective function or weighted sum of the objective function, and they show that it's going to lead to some fair solutions. This algorithm, it's easy to see that if Q goes to infinity, this is equivalent to agnostic federated learning. In this work, motivated by ensuring fairness among users and robustness against malicious adversaries, we propose to see federated learning as a multi-objective optimization problem. Just take a look at this definition from Wikipedia for multi-objective optimization, and lots of things becomes clear why we are using this framework. Multi-objective optimization is an area of multiple criteria decision-making that is concerned with mathematical optimization problems involving more than one objective function to be optimized simultaneously, where optimal decisions need to be taken in the presence of trade-off between two or more conflicting objectives. And keep this in mind. And here, the next sentence is what we want to do. In federated learning, we treat each user function fi as a separate objective and aims to optimize them simultaneously. And you can see that basically our definition for federated learning, and this one, it's really matches. So this is, it seems to be a right framework to tackle the problem or approach the problem. And later by simulation result, we will see that we confirms that our approach is the right one. Formally, we want to minimize this f of x, which is a vector. Here we are no longer talking about the single objective values. We are talking about vectors. We are in the vector optimization framework. And each element of this vector is one of the user's objective function. For example, this one belongs to first user, and then second user, and the objective function of the last user. And then we want to minimize this objective function with respect to partial ordering. And partial ordering is if f of x is smaller than f of I, all the elements of f of I, basically we compare them element-wise. For fi, f of x should be smaller than f of y. In the vector optimization, unlike single objective, there might be cases that we have the following situation, which basically we cannot compare the 2 points with each other. For example, we cannot compare x and y.
May I interrupt you, Kiarash? Can you elaborate a bit more what this partial ordering is coming and why it is there, and why it is necessary?
Okay, the question is we have two solutions. And our question is how we can, let's say an oracle give you two solutions, how we can compare these two. In a single value optimization, we know how to compare them. But when it comes to a vector, how we should compare two vectors with each other, how we should compare, that's the question. And we propose, we use partial ordering, and we will see we can do other orderings instead of this particular ordering. However, this is what we use in this paper, and this is natural, and lots of problem in this domain using this ordering. I have a slide about how we can define ordering,
and then you compare pairwise, and this is you try to respect the ordering that you found on each set of data of users. This is how you handle it?
Yes, it doesn't mean that we always do that. This is the way that we define how we compare two solutions. Okay, we need to, when we have a framework, we need to say, okay, I'm giving you apple and orange, which are not naturally comparable. However, I'm telling you that you can use their weight to compare them. This is a way of me telling you how I'm going to compare x and y in a vector space.
Okay.
This is definition. Let's say this is definition.
Okay, you start with that. It doesn't have this as a motivation. You want to start with something. You start in this scenario. Okay.
Yeah, exactly.
Thank you.
And then we need to define what is an optimum means. An optimum in vector space is called Pareto Optimal. Basically, X star is a Pareto Optimal solution of this vector optimization if its objective value f of x star is a minimum element with respect to partial ordering, or equivalently for any x, if f of x is smaller than f of x star implies that f of x is equal to f of x star. In other words, just put this in word. This means that the Pareto optimal solution is a solution which is not possible to improve any component objective in f of x star without compromising some other objective. And this is good, and we are interested in this because it immediately enforces fairness among users in our setting. Basically, we don't want to improve some users by sacrificing the performance of other users because it's not fair. Regarding Wahid's question about partial ordering, one important characterization of a partial ordering in a real linear space, which has some definition, is that this ordering is always induced by an ordering cone. You can see this theorem, and the essence of this theorem is that when we have if we have a cone in a space, we can define partial ordering with respect to that cone. For example, you can see here, if C is a convex cone in X, then the arbitrary relation that we define it here for X and Y is defined if X minus Y belongs to this cone, and we will see it later with an example. What does this mean? Here you can see an example of a pointed cone, and by pointed it means that if C and minus C, we take their union, they are only the only part that it's shared between them, it's a zero of the system. We discussed partial ordering. The partial ordering, the element-wise partial ordering that we discussed is called a natural ordering cone, and you can see it here. And basically, it's a positive quadrant. And you can see it in this figure. Consider that we have two objectives, F1 and F2. In this space, if we want to use element-wise ordering, then we have this cone. And we can compare points. How? Based on the definitions before, let's say that we want to compare B with some points. We put the cone here, and we can compare this point with all the elements in this cone. For example, let's compare it with C. We can see that B is a better solution than C. Well, because in both terms of F2 and F1, B is a better solution. We can do the same if we put this cone here between A and C. We can see that A is a better solution than C in terms of both objective. However, what do we need to see? Here we see that y minus x, if you want to have this relation, should belong to our cone. And here you can see that A minus B or B minus A do not belong to this cone, so we cannot compare these 2 points. That's the case that I mentioned before, that not necessarily we can always compare points. And it means that we have a set of Pareto Optimal. We might have a set of Pareto Optimal solution, or sometimes they call it Pareto front. In this work, we assume all objective functions are continuously differentiable, but not necessarily convex to accommodate deep models. And just remember, finding a global optimum is difficult in single objective optimization. We have the same challenge here. Finding a Pareto Optimal solution is difficult. So instead, we settle with a weaker notion, which is defined here and is called Pareto Stationary. We call X star a Pareto stationary solution if and only if there exists some convex combination of gradients that equal to 0. And we can show that if we have a Pareto stationary solution and all the objective functions are convex, then our solution is a Pareto optimal. Basically, the relationship between Pareto stationary and Pareto optimal is analogous to a local optimum versus global optimum. So far I have discussed that what is our objective, what kind of solution we are looking for, and how we define a minimum in this vector space. However, the question is how we can find such a solution, how we can find a Pareto stationary solution. We can use an algorithm which is called multiple gradient descent. Basically, MGDA leverages the KKT condition to find a direction that is common to all objective. It does it by solving this quadratic problem. And if you want to see it, by solving this, we come up with some weight in each. We find lambda I in each step. And by combining the gradient based off these weights that are adaptively chosen, we can find a common direction for all objectives. This optimization is basically equivalent to finding a minimum norm point in the convex hull of the set of input points. And MGDA has theoretical guarantee to converge to a stationary solution under mild assumption. Just to see what does it mean to have minimum norm point in a convex hull of gradients of set of points. Consider that we have two vectors, red one and blue one, and we want to find the minimum norm in this situation. The minimum norm element would be the in this case it's the blue one. The other case that we have this situation is the red one, and this case the middle one is more interesting. When we have the situation that they point into different direction, you can see that the minimum norm is this black one, and you can immediately see that if these two vectors point in the opposite direction, the minimum norm will be 0. which means that this solution is a Pareto Optimal, Pareto Stationary solution. Another way to see this optimization problem is to see it in the following way. Basically, this optimization is a dual form of the following primal form. Let's say that we have the gradient, and we remember that if we want to improve some function, we try to find a direction that basically reduces the function. In single objective, that direction is opposite to the direction of the gradient. So here we want to minimize this. And because we have different values, we want to find the maximum and find the minimum of that. Basically, this is nothing but line search. That's the problem. And if we, with some reformulation, we can drop this. We can drop this term, and we can write the problem in the following way. We can bring this part to the constraint, and we can easily see that this is the primal form of this dual form. So basically what we want to find is to find a decent direction that works for everyone. This is no magic. Basically, that's based for definition. We solve this problem, and then we find a common direction. And then another way to motivate why we are using MGDA, if you remember, I have already mentioned to you that we have AFL, Agnostic Federated Learning, that tries to minimize the worst case loss. We can rewrite this objective in a new form. Just consider this problem here and ignore this part. We can see this part, this minimax problem, it's exactly the AFL algorithm. And if we adaptively center the user function using function values, and if we add this, we can, with some, and if the functions are smooth, we can replace it. We can use the quadratic bond, and we can get this formulation. Where J here, it's a Jacobian matrix. Remember that our objective is a vector, and if we take its gradient, and if we take the Jacobian, we will end up with a matrix, which we call it J of F. And here, because the problem is, we can swap minimum and maximum in this problem, since the problem is convex in X and convex in lambda, we will end up with this formulation here. And if we solve this formulation for X and set its derivative to 0, we will get this, setting here, which is exactly equivalent to the problem to MGDA problem that we discussed before. Basically, this make a nice connection between our algorithm and AFL. AFL tries to optimize the worst case loss. What we do here, we do a similar thing. However, we adaptively center the function. We remove this part from it, and that's why our algorithm inherently is more robust. We will see it later in the experiment section. So with this introduction, we are ready to introduce the final algorithm. The final algorithm is called FedMGDA. Basically, in each communication run, we select a subset of clients, not all of them, subset of them. This is to model that not all users participate in a real application in training a model. Then we ask them to send their update or gradient. Let's call it G. We normalize the gradient. We solve the following we solve this quadratic problem, and by using the lambda from here, we find a decent direction and update the model. And the model we use for our user is a simple model. Although it doesn't matter what kind of model we use, but we use a really simple model. Basically, we ask the user to split their data into R batches, go over all the batches to update the model, and repeat this process k times. And at the end, what we sent back is not exactly gradient. It's basically the difference between the received model and updated model. We could also send back gradient. There are some results that we show that sending back gradient is also good. Before going to the next slide here, I need to mention that we do a normalization step here. The reason for that is we already showed that MGDA is robust because it adaptively removes it's basically recenter the objective function. However, there are another types of attacks that they try to scale the function. Basically, the previous one is good for bias. However, they might scale the loss function. And this simple normalization step surprisingly prevents lots of attacks on distributed system. Also, we have a new constraint here. The reason for adding this constraint is just remember FedAvg. FedAvg, the original problem, the original algorithm, is designed to optimize average loss. And our algorithm is designed for fairness. But what if we want something in between, or what we should do? We basically, we add this constraint and limit the amount that lambda can deviate from lambda 0. It's some preference vector. And in the case of FedAvg, it's going to be 1 over m. And in this way, we can have and by controlling epsilon, we can have a smooth interpolation between the two algorithms. Here, just see that if we set epsilon to 0, we can recover FedMGDA. Sorry, FedAvg. We show the convergence of our algorithm. We show that with some technical terms that you can, technical conditions that you can see here. The Jacobian multiply, the norm of the Jacobian multiplied by lambda, which is the common direction, or we can see it as the gradient. Norm of the gradient goes to 0, which shows that the algorithm goes to a stationary solution. And also we showed that under some technical condition that you can see it here, and with this step size, our algorithm converges to the closest Pareto stationary solution. Also, let's take a look at the experimental results. For the first experiment, we run our algorithm. The task is image classification. We run our algorithm on Federated EMNIST, which is a standard federated learning data set. This data set consists of images of digits and English characters, both lower and upper cases, with 62 classes in total. The images are partitioned by their authors, which naturally makes the data set non-heterogeneous and unbalanced. Number of clients, we have 3,400 clients, and the number of trained sample is 700,000 samples. We measure the performance of algorithm and, or we compare the performance of our algorithm on two different values or two different measures: average performance and standard deviation. Average performance, we all understand that we want the average performance of our algorithm be high. And the standard deviation is a way of measuring fairness among different users. So the smaller the standard deviation, it means that the algorithm is fair and the solution is basically consistent among different users. We compare our algorithm with FedProx, with FedAvg, and FedProx, which is FedAvg when a proximal regularizer is added to each user, QFedAvg, which uses QFair idea, and some combination of our algorithm with different algorithm. For example, our algorithm is FedMGDA plus. FedMGDA is a naive implementation of the algorithm, and MGDA prox is FedMGDA plus proximal regularizer. You can see that the best performance in terms of average accuracy can be achieved by our algorithm, and also in terms of standard deviation, our algorithm achieves the smallest value, the smallest standard deviation, which shows that it's more fair toward all the user. In particular, this is expected. However, this one that we can see that the average performance is good. It's kind of interesting because we do not optimize it, but we get it because if we have a solution, if we have a model that works for everyone, which means that we are learning something, and then it can be translated to better average performance. To test the robustness of the algorithm, we discussed that okay, let's put it this way. Most of the attacks on distributed system can be reduced to two fundamental things. I'm not saying that all the attacks are using this pattern, but they can be reduced in somehow in the following two simple elements. Either they are trying to add a bias to the loss function, or they try to scale the loss function in order to take advantage of the system. So we consider both cases. We already discussed that AFL algorithm is vulnerable to attacks, adversarial attack, and in particular is vulnerable to both shift and scaling. In this case, the first experiment, we compared AFL and QFedAvg. And our algorithm on adult dataset using attack, which we call it bias, basically, or adversary. We have a single adversary that add a constant to its loss function and tries to get a better performance for to shift the performance of the algorithm toward its local dataset. In this case, we use adult dataset, which is a highly which is a data set that has 99 features, binary features, and has information, some features for some adult users, and we try to predict the salary of the user. There are two main features here, whether the data set is whether that particular adult has PhD or non-PhD. Basically, there are 32,000 samples for a non-PhD user and 41 samples for PhD users. Adults with PhD. I explained the bad way. So the data set for this feature is really unbalanced. So that's the way that we divide this data set into two users. One user has only data from PhD set, and the other one has data from non-PhD. It's natural to assume that the one with the smaller amount of data try to take advantage of the system. So we add bias to that to the PhD user or PhD data set or PhD client, whatever we call it, that has only data from that particular class. And we can see the two cases, before attack and after attack. The solid bars represent when we have for example, the red one represents FedMGDA and this yellow one represents AFL. The solid one shows the case without attack, and the dotted bar shows after the attack. What you need to notice here is that after the attack, you can see all the performance of all the algorithm drops except the FedMGDA, which expected because we do that, we recenter the loss function, so that's why our algorithm is robust. I mentioned to you that we do gradient normalization in order to prevent scaling attack. Scaling attack is when user artificially multiply its loss function by a big value. Same as before, that here we measure the performance before and after the attack. The data set is CIFAR10. We have 100 users, and the task is image classification. And we have only one user that tries to take advantage of the system. Here you can again see that the performance of the different algorithm when they are not using that MGDA and this normalization, all of them they drop. In particular, the performance of algorithm like fair federated learning, it drops the most because they use some information regarding the loss function, which makes them vulnerable to adversarial attack. Also, motivated by real-world application of federated learning, we define a new type of fairness for federated learning, which is fairness during training. Previous concept of fairness, first of all, we do not have a universal definition for fairness. In federated learning, people measure it by measuring the standard deviation of error for different users, but there are a whole bunch of other definitions for fairness. However, this fairness that we define here is different from those other definitions in a way that they are applied to when the model is trained and to the final result. However, our fairness is going to be applied during training. What does that mean? We want to ensure that when users participate in a training process, the performance always gets better, and we do not sacrifice their performance. And to see why it's important, consider that we have a couple of hospitals, and they can decide whether they want to participate in a training process. The minimum thing that we can ensure to them is that if you participate in this process, your performance is constantly getting better and better. Otherwise, there is no motivation for them to participate in a training process. We have two cases. One of them again, in this case, the data set is CFAR10. We have 100 users, and each user has 500 image samples. We divided the data in a way that no user have data for more than 5 classes. Just CFAR10 has 10 classes of 10 different labels, and no user has data for more than 5 classes or 4 labels. We do 2 cases. One is when we use full gradient. We use all the data to calculate the gradient. And the other one is we update the model by small batches. And at the end, what we return to the server is the difference between the received model and the updated model. The right one represents when we exactly calculate the gradient. You can see after the initial phase of training, algorithm 2R, when it gets kind of stable, the performance of a participating user is constantly improved, or at least it does not get worse. Here we show that the percentage of the user that participate in a training round, how many of them, or what percentage their performance get improved. You can see that algorithm that rely on MGDA or multiple gradient descent, they can ensure that 100% of the users, their performance gets better. When we have the case that we have a small batch size because we do not exactly calculate the gradient, we can see that we can no longer guarantee 100% improvement. However, still the MGDA-based algorithm achieves the best fairness, or improves the highest number of user in each communication round. And with this, this presentation is over. Thank you so much for listening. Please go ahead if you have any questions.
Sure. Thank you very much, Kiarash. Yeah, we can go one by one. There are like 2 questions. I also have myself some questions. So let's start with Tim. So please open your video and your microphone and ask your question.
No, sorry, I didn't have a question. I was just like saying thank you with the clapping.
So we had 2 other friends also who raised their hand. I wonder if you have questions. Well, you can open your video and ask your question. Or maybe it was a mistake too. So then I can go with mine. So meanwhile that you think of your questions, I go with mine. So Kiarash, thank you first. It was quite detailed talk. Can you get back to where you formulated this multiple gradient descent? I think it was like page 12. It was early that you have these lambda i's there. I think, yes.
Oh, multiple gradient.
Yes, here. You just passed it, yeah.
Okay.
12, I think. It was 12. One further.
Or this one.
You have that lambda I formula. Yeah, this one, 13.
Okay.
So here, it seems that you try to have like two steps, right? In one step, you find the gradient of the user. In the second step, you try to find the lambda I to see how to solve the problem, right? So it's like you divide this federated learning problem instead of going only to gradients, having to gradients also the weights. You mentioned that if you use lambda I to be equal like lambda 0, you're getting back to FedAvg that is already suggested in the literature. So somehow you're generalizing FedAvg. Even maybe you get lambda I ni divided by n, you get the weighted version, which is not necessarily the FedAvg, but weighted FedAvg, right? I have this question that can you produce the agnostic version with this one as well? Like minimax problem that you mentioned?
The agnostic version.
So I was thinking that maybe if you get lambda equal 1, the other 0, then you have just one weight. So you pay attention to one user, you ignore the others. But if you want to pay attention only to the maximum one, then you need that like lambda I to be equal 1 to actually take care of the maximum. So then perhaps you can reproduce agnostic too. It's not like a fixed weight. It depends on the maximum of the gradient, right?
Vahid, the answer is here. We cannot exactly recover agnostic one because in each step we do this subtraction. We adaptively center. That's why we cannot exactly recover agnostic federated learning, but we can see that our result is even better than agnostic federated learning because it's more robust. And I haven't included the result in terms of fairness comparing our algorithm with agnostic federated learning or algorithm. At least I can say it's comparable if it's not even better. Okay, and one thing that I like to mention here is that you mentioned that the original one, when we have some fixed weight, that's called linear scalarization of the objective function. In some cases, that could lead to some good result. However, the condition is the objective function should not compete with each other. If the objective functions are competing with each other, using a fixed point from the beginning does not lead to a good solution.
And this is usually the case, right? Because it depends how the data evolves in each user. So you don't have the fixed version, so you never know.
That's definitely true.
If it's not even competing now, it doesn't mean that it doesn't compete tomorrow, right?
Yes, that's true.
Okay. All right. So thank you very much again, everybody. Do you have any further questions that you want to ask? Otherwise, I don't see that somebody raising hands. So I think that thank you very much, Kiarash, for the detailed talks you gave us today.
Yeah. Thank you and the Gerard Institute for inviting me, and also thank you everyone for coming and joining this talk today.
Thank you. Thanks, Kiarash. Bye.
Bye.
Thank you.